Let's do a quick review over logarithmic and exponential functions. An exponential function is a function that's written in this form: f of x equals b to the x, where b is your base and x is your exponent. B cannot be equal to 1, of course, because 1 to a power is 1. A logarithmic function is usually written like this: f of x equals log base b of x. Now for both of these, for the logarithmic or the exponential function, you can write as y equals b to the x, or y equals log base b of x. And so this logarithmic function is actually based off of the exponential function. I mean, both of these, y and y, both of these are equal to b to the x and log base b of x. A lot of times you just see your logarithm, if you're trying to evaluate one, written like that, just log base 5 of 10 or something like that. So, you know, if you want to change this over to this form, it's a little tricky, because what does this actually mean? What does the logarithmic function actually mean? These usually confuse the students at first if they've never seen them. I've had students ask me, you know, why even use logarithms? And logarithms it's just another way of writing something to a power. So this is what I do if I'm dealing with exponential functions and logarithms and I'm getting kind of confused. I write down this right here: y equals log base b of x means b to the y equals x. That's what it actually means. And so you have to really relate logarithms back to exponentials to kind of understand what's going on if you're trying to really understand the whole, you know, what's going on with a logarithm. Some of the properties of logarithms that you may or may not know: if you take log base b of a product, say m times n, so if you take the log of any product, you can rewrite that as log base b of m plus log base b of n. This is called the product rule for logarithms. All right. And you can go backwards. As long as this base is the same, if you're taking the log of something plus the log of something else, as long as the base of the logarithm is the same, you could write it as a product. Okay? We also have a quotient rule. For logarithms, and it states that if you have log base b of a fraction or a quotient, say m divided by n, and that's equal to log base b of m minus log base b of n. And again, you can use that in reverse. If you have log base b of m minus log base b of n, that is equal to log base b of the quotient. And probably the most powerful thing about writing something as a logarithm is the next rule, the power rule. The power rule makes logarithms really, really powerful, no pun intended, because if you have log base b of, let's say, m to the n power, then logarithms, the way they work, and because of the way that they change over to the exponential function, they allow us to take the power and move it in front. So that's equal to n times log base b of m. And that's extremely powerful, especially if that power, that exponent, is a variable. Being able to move a variable power down allows us to be able to take derivatives and things like that a lot easier. So that's a very, very important rule, the power rule. The other rules are important as well because they could help us take something that seems maybe a little confusing, like some big function that's a quotient, and break it up into two smaller functions, and then from there we would be able to take a derivative or an integral or something like that. So applying product rules and quotient rules and power rules, is as long as we are dealing with logarithms, can make derivatives and integrals a lot easier. Okay, and so that's why we're even going over this. There are a few basic properties of logarithms, like log base b of 1. No matter what the base is, if you evaluate 1, the logarithm of 1, so it could be log base 10, which is the understood base, like if I didn't have a number down here as the base, log base 2, log base e, which I'll get into in a minute. If you evaluate 1, that's always equal to 0. The reason for that, if I had y equals log base b of 1 and I changed this over to an exponential, then that would be b to the y equals 1. And so when can you raise something to a power and always get 1? It's when the thing is equal, when y is equal to 0. Like x to the 0, 1 to the 0, 5 to the 0, all of those are equal to 1, right? And so that's why if you take log base anything of 1, you always get 0. So if that seems a little confusing, just remember, like log base 4 of 1 equals 0. Log base 10 of 1 equals 0. Log base e of 1 equals 0. So any of those evaluated at 1 will always give you a 0. And again, it's because, like over here, if I was to put these numbers in, I would have 4, let's see, wait, Yeah, the base is 4. So 4 to the y power equals 1. This means 4 to the what power equals 1? Well, 0. So that's why over here log base 4 of 1 is 0. They're always equal to 0 if you evaluate 1. Alright, so this is one property. Log base b of b to the x. That's always going to be equal to x. So if the base of the logarithm and the base of the number, if those both are the same, then the answer is the power. Okay, so you may say, well, why? I gotta know why. And that's okay. It's good to know why. If I was to say y equals log base b of b to the x, and I change this over to exponential, then what would I have? This b to the y power equals this, what you're taking the logarithm of, which is b to the x. So y is equal to x, because both of these are the same. So that's why we always get that x there. Okay? That seems confusing. Really what we're looking for is, does the base of the logarithm and the base of this, can they be written as the same number? If so, the answer is just the power. Okay. And it's really, the property is usually just written like that. Usually there's not a y in front. I'll write a y equals in front because I'm showing you y.
That's called the X property, power property, or what?
It's just another property of logarithms. Just a property. The last property of logarithms is if you have a base raised to a log of that same base of x power. So these look a little strange because you have a logarithm in a power. Well, if this base right here, that's what you're raising this power to, and the base of the logarithm here, if they're the same, then the answer is just equal to x. So this is b to the log base b of x power, just equals x. Okay? So that's logarithms. Well, I would be willing to bet that everyone in here, even if your calculator doesn't have a log button, or you've never seen a log button on a calculator, you've seen something called LN on a calculator. LN, what does that mean? That is natural log. And so natural log must be pretty important if it has its own button on a calculator. And it is. It is the special logarithm. Log base e. Log base e is natural log. Does everyone in here know what e is? Sort of like pi, that's right. It's a transcendental number. And a transcendental number is, it's a symbol that stands for a number. And that number is something that occurs in nature, just everywhere. If you saw that in a physics book and you were approximating, or if it was an application problem, that'd be like 2.71828 something something something. and it just keeps going on and on forever, just like pi. Okay, so log base e is natural log. And so since it is that special logarithm, let's see if we can apply natural log to these properties real quick. So what do you think the natural log of 1 would have to be equal to? 0. Because this is log base e of 1. So log of 1 is always 0. So natural log of 1 is no different. Okay? What would the natural log of e have to be equal to? Well, remember, what is natural log? It's log base e. So what is log base e of e to the first power? 1. All right, do I need to write that down? Log base e of e to the first power. These match up. The answer is the power. Okay, so just real quick, what is the natural log of e to the third power? 3. Okay, so whatever the power is, if you take the natural log of it, and it's e there, that's the answer is the power. Okay, and also e to the natural log of x then would have to be equal to, if that was log base e, that's right, x. Going back to this previous problem, if I wrote it in variable form, what if this was the natural log of e to the x? What is that equal to? X. If you look at these two problems right here long enough, and you have a really good algebra background, you probably notice something. I won't ruin it for you, but these two right here, because of what these are both equal to, that is a special property. And when two functions have that special property, well, you can look that up. That's something good for you to look up. We'll eventually cover that, if not today, tomorrow. That's a good property there. I won't ruin the surprise. All right, so logarithmic functions and exponential functions can be related just like that. Y equals log base b of x means b to the y equals x. Alright, and so if just because we throw e in there as a special logarithm doesn't mean anything changes. Y equals log base e of x means that e to the y equals x. Alright, now all of these rules with log base b, they still all apply with natural log, because natural log is just a special logarithm. So the natural log of a product is equal to the natural log of one of the factors of the product plus the natural log of the other factor. The natural log of a quotient, again, same thing. Natural log of the numerator minus natural log of the denominator. The natural log of, let's say, x to the n power. This will be the power rule. Just because it's natural log doesn't mean it's anything different. You can still move that in front. So that's n times the natural log of x. So if you take a logarithm and it's written as, say, one term like this, let's say I had the natural log of 2x squared over z, which we won't have multiple variables like that in our problems usually, but we can expand this. So if I wanted to expand this logarithm, then the way you would do that, first you apply the quotient rule. So you can say the natural log of 2x squared minus the natural log of z. Then once you've applied the quotient rule, if you can apply the product rule, you want to do that. And I can with my first term here. So that's the natural log of 2 plus the natural log of x squared. I still have minus natural log of z. Then the last thing you want to do is apply the power rule if you can. So that's the natural log of 2 plus 2 times the natural log of x minus the natural log of z. Now you should and that's this logarithm completely expanded. So think about this. Think about where you've taken derivatives of quotients. If there was some way that we could write a function using natural log and then expand it like this into different terms, what do you think would be easier to take the derivative of? I mean, you know this by things you learned in Cal 1, was that when you take the derivative of quotients or fractions, a lot of times those take a lot longer than, say, taking the derivative of a constant or taking the derivative of just x or something like that. And so taking derivatives with natural logs are the same. They're easier if you can expand them. Okay? Or any expression is easier to take the derivative if you can write it as simpler terms. And so that's how we use logarithms sometimes with derivatives or the properties of them to help rewrite them to make it easier or to make it simpler. Okay? And so this is called expanding, and I put expand in this, expanding a logarithm. That's where you take a fraction, a quotient, a product, whatever, and you make it as large as possible. Now, you can take that same logarithm, this one right here, and I can condense it. More spelling problems. And so, to condense a logarithm, the first thing that you do is you look and see, can I apply the power rule backwards? Are there any numbers in front of logarithms? And if there are, you can take that number and move it up to a power. So I can say this is natural log of 2 plus natural log of x squared minus natural log of z. Alright, now once you have a bunch of terms in a row that are all natural log or logarithms, then you want to look at the signs in front of all of those logarithms. Any logarithms that have a positive sign, whatever you're evaluating the logarithm at, you put all of those terms in the numerator of a fraction. Any logarithms that have a negative in front, you put all of those terms you're evaluating in the denominator, and you make a product of all of those terms. in the numerator and in the denominator. So you see these two are positive here. So if I wrote this as 1 logarithm, it would be natural log of 2 times x squared. And then this one is negative here, so you put that one in the denominator. If there would have been another term out here, say it would have been like minus 3, then I would put a 3 in front of the z here. So if it's a negative logarithm, then you put that in the denominator. If it's positive, you put it in the numerator. Now, you cannot take the logarithm of negative numbers. So that's just by definition, the way that it's defined, it doesn't work. You can try to plug some negatives in there and see if you can get it to work with the way it's defined with exponentials. It doesn't work. So you never want to take the logarithm of a negative number, or try to. So you can use those properties to help solve logarithmic or exponential equations. Say that I had, let's see, 9e to the 2x power equals 13. I can solve for x here by using some of those properties. And again, this isn't using any calculus at all. This is just algebra. To solve for x, we have to figure out a way to get the e to the 2x by itself first. And so I would divide both sides by 9. Alright, and so I have e to the 2x equals 13 over 9. Now, to get this x, this 2x term by itself, what you can do is take the natural log of both sides of the equation. What you do to one side, you have to do to the other. And so by taking the natural log of e to some power, do you remember this property? Natural log of e to some power is equal to the power. So I have 2x equals the natural log of 13 over 9. Okay. And then to get x by itself, you divide by 2. Alright, so this is the decimal answer, I'm sure, that you would get. Now you could simplify this a little bit if you wanted, you know, because this isn't real pretty right here. And since you're dividing by 2, that's the same as multiplying by 1/2, right? So this is 1/2 times the natural log of 13 over 9. And then remember, what can you do with numbers in front of natural logarithms? You could bring that there. So this x is actually equal to the natural log of the square root of 13 over 9. Okay. Now you could go further and simplify that. That's the natural log of the square root of 13 over what? 3. Because when you take the square root of a fraction, you can take the square root of the top over the square root of the bottom. Alright, so that would be probably the most simplified answer. Of course, you didn't really, if you just wanted to solve for x, you wouldn't have to do any of that. If you were looking for a decimal, all you'd have to do is, in your calculator, say 13 divided by 9, then hit your natural log button. Whatever that gives you, divide by 2, and you have what x would equal. So, but we're using logarithms to help solve equations. You could also solve an equation like this using the other properties. Let's see, maybe the product rule for logarithms. You could use that help you solve something like this. Log base 2 of x plus 3 plus log base 2 of x minus 3 equals 4. We can figure out what we would have to plug in and evaluate this logarithm at to give us 4. Because we know that if we have a plus right here, then I can apply what? The product rule backwards, right? So this is equal to log base 2 of x plus 3 times x minus 3. Okay? Once we've applied that logarithm logarithm property, then what you can do is change this over to an exponential. Right? You remember this? I said y equals log base b of x means that b to the y equals x. And so if I change it from this form over to this form, my base is 2, so this is 2 to the 4th power equals x plus 3 times x minus 3. Or 2 to the 4th is 16 equals, that's going to be x squared minus 3x plus 3x, those cancel out, and then minus 9. So I have x squared equals, when you move the 9 over, 25. Take the square root of both sides, so x equals what? Plus or minus 5. Now the tricky thing with logarithms is, though, if you solve a logarithmic equation, once you get your answers, I got a plus and a minus 5, I need to plug them back into my original and make sure that I'm not trying to take the logarithm of a negative number. Because you see, if I go back and I plug that in, plugging in a 5 is okay, but plugging in a negative 5, I'm trying to take the logarithm of negative stuff if I do that. So my only answer is x equals positive 5. So with logarithmic equations, you do have to always go back and check. Now just to give you a taste of what is to come in section 5.1, I want you to think about this. Now, we went over the power rule for integrals, right? We said that if we're integrating something to a power, that you add 1 to the power and then you divide by the new power. Alright? So, what happens if I have the integral of 1 over x, then I rewrite that as x to the negative 1. Now, if I was to add 1 to the power here, that would be x to the 0 divided by 0. And with that, so all types of bad things happen. I can't do that. Alright, so since I can't do that, there must be something else going on here. And there is. The integral of 1 over x dx is actually defined as the natural log of x. And so if I have the function natural log of x, the derivative of the natural log of x then would have to be equal to what? 1 over x. the derivative of natural log of x is equal to 1 over x. So that means that, let's say that I had y equals the natural log of u. So the derivative of the natural log of u is going to be equal to 1 over u times the derivative of u. And that's where we will pick up next time.